Today we're going to start in on Chapter 18. We're going to do sections 18.1 to 18.4. In the beginning, we're going to talk about electrophilic aromatic substitution. That's going to be the bulk of the reactions we're going to talk about in this chapter. Because benzenes are so stable, reactions that preserve that stability of the aromaticity are favored. So the most common thing to do with benzene rings is to replace one of the hydrogens with what we call an electrophile, an E. So I'm going to write E here. That E stands for electrophile. That's why we call it electrophilic aromatic substitution. There are lots of different things that can be electrophiles, but most of them can fit into 5 different categories. So our 5 examples of electrophilic aromatic substitutions are, first, halogenation. So you can imagine with halogenation, you replace your hydrogen with X, so some sort of halogen. Our second example is called nitration, and you're going to replace the hydrogen with NO2. Third one is called sulfonation. And in sulfonation, you replace that hydrogen with SO3H. Our fourth one, there are 2 different kinds of Friedel-Crafts reactions. This first one, Friedel-Crafts alkylation, replaces that H with an R group. So some sort of alkyl group. Our fifth type of reaction is called Friedel-Crafts acylation. And so in that case, you replace that hydrogen with what we call RCO. And if you draw it out, it looks like R carbonyl. That's where it gets attached. So those are our 5 possibilities that we're going to look at. We're not going to talk about all of them today. We're going to spread it out over a few days, but I wanted you to get an idea of where we're going. The mechanism of these reactions is similar. And so essentially what happens is you take your benzene ring with its hydrogen and a double bond attacks your electrophile. So your electrophile may be positively charged or it may just be attracting electrons, but that's your electrophile. And the intermediate for that looks like this. So you still have your other 2 double bonds. You have your hydrogen, your electrophile adds on to the carbon with that hydrogen, and there's a carbocation down here that is formed because the double bond leaves. In the last step, a base comes in, removes the hydrogen, and these electrons go to reform the double bond, so you're reforming your aromaticity. That's the driving force for these reactions. And you have an electrophile on where you had a hydrogen before. You'll notice in the intermediate here we have a carbocation. This carbocation can undergo resonance, and so you can get the carbocation shifting over here, or the carbocation can shift up to here. These are going to make a difference later on when we start adding on substituents to our ring and do electrophilic substitution on rings that are already substituted. So always draw on the hydrogen that's on the carbon that you're substituting with an electrophile so you can keep track of it. That positive charge that I drew for the carbocation is always going to be ortho or para to where your electrophile is. It's a two-step reaction, and the first step is rate determining. So let's see some examples of what this looks like. First one is halogenation. So with halogenation, you have to have a Lewis acid catalyst. In that case, it's either FeCl3 if you're adding chlorine, or FeBr3 if you're adding bromine. The mechanisms are going to be the same, but you need that catalyst. So your first step generates an electrophile, and then the electrophile is ready to add to the ring. So let's do it for bromine. You take Br2, you add FeBr3. So the reactants in this reaction would be Br2 and FeBr3. That's what you would have on top of your arrow. Your electrons from your bromine are going to attach to this iron because it's a Lewis acid. So now you have Br, FeBr3, and your FeBr3 is going to have a negative charge. This Br in the middle is going to have a positive charge. So that makes it an electrophile. It's easier to be attracted by the aromatic ring. So you're going to take your aromatic ring, and here's your hydrogen. Here's our activated electrophile. And your ring is going to attach this Br, and these electrons will go back onto the Br+. And so you'll end up with a molecule that looks like this, where you have a hydrogen here with its Br, and you have a carbocation down here. This can form resonance structures just like we saw before. And then in the end, our base is the thing that came off, right? BrFeBr3 minus. Okay, these electrons can come and remove a hydrogen, and these electrons can reform the aromatic ring. And so your major product of this reaction is brominated ring, HBr, and FeBr3. Your catalyst is regenerated. If I asked for the major organic product of this reaction, all you would need to do would be to include this one right here. Let's talk about nitration and sulfonation next. Again, with nitration, we need to form our electrophile. And so nitration happens with nitric acid and sulfuric acid. Those are your reagents. So we take our nitric acid, which looks like this, and then we can take our sulfuric acid, which is an even stronger acid, and we can protonate our nitric acid. So now we have a good leaving group. This water can leave as a leaving group, and your NO2 is left. And so from this step you have water, and you have NO2 plus, which is an electrophile. That can add to the ring, just like our electrophile added with our halogens to the ring. If we wanted to do the same thing with sulfonation, so this one was nitration, and your ring ends up looking like this. with an NO2 on it. Sulfonation involves sulfur, obviously. And so you're going to take sulfur trioxide and sulfuric acid, H2SO4. Those are your reagents, H2SO4 and SO3. So if we redraw H2SO4 like this, then our electron pairs can attack the hydrogen, which then attacks the oxygen. There's your sulfur. And now we have our electrophile. So SO3H is our electrophile. And it's positively charged, so here it goes. And you end up with a benzene ring with SO3H. This is a precursor to things like sulfanilamide, which is an antibiotic. I'll draw you a picture of that. This is sulfanilamide. So you could see how we could create that from our SO3H. It just gives you an idea of how it's used in reality. This is the end of our talk for today, and we will dig into more on the next one.